Welcome to my channel. This is lecture number 11 on adaptive signal processing course. In this video, we'll continue our discussion on gradient descent algorithm. This is part 2, and in this video, we'll be discussing finite sample 1D examples. In previous lecture, we have discussed the basic concept of gradient descent algorithm that is used to minimize 1D analytical function. So in analytical function, we imply that the cost function is defined by one equation. Here, the cost function is considered as convex analytical function, and it is having only a single variable, say it is w. In that case, the cost function is g of w. So we have considered this example. The g of w equals to 4w squared minus 3 of w plus 13. So this cost function we have discussed, and our objective was to find the optimal parameter w star, which will give us the minimum value of this cost function g of w. And for this example, the w star is given by 1.5. That we have discussed in detail in the previous lecture. So in last lecture, we have discussed this quadratic cost function and this minimization problem. There we have shown that if we consider one cost function, this kind of cost function, then we can find one iterative algorithm of this form, that w of n plus 1 should be wn plus 1 correction term. And here this correction term, so you see this one, its sign of this correction term is just opposite of the derivative of this cost function at that point wn. So that thing we have got from this logic, that at w star it is having minimum value. Suppose if we consider one point here, which is left side of w star, that time our derivative is negative, and negative imply that this cost is decreasing at that moment. Okay, so here derivative is negative, it's implied that this function is decreasing at this point. That means we should move forward, means in positive direction, this direction, then only we can minimize the function. So it's implied that at w1 the derivative is negative and we should add some positive value. Similarly, on the right side at w2 derivative is positive, that means function is growing. That time we should reduce something, means correction term should have some negative value, then only it will move towards optimum point. So whenever the gradient value is negative, we should add positive component correction terms, and when gradient or slope is positive, then we should reduce something. That means we should subtract some value from this current position, then only we can move towards w star. So combining these two, we can say that sign of the correction term is the opposite of sign of this derivative. And again, the magnitude of this correction term we can make proportional to the magnitude of the derivative, because if the derivative value is large, that implies that the point is far away from the optimal point. At that time, we can have a larger step, larger correction term. we can add it. And when point is closer to the optimum point, then we can add very little correction terms. Then also we can move towards W opt or W star. Thus, the magnitude should be made proportional to the magnitude of the slope. So combining these two, we have discussed that the correction term is actually proportional to the negative of slope or negative of gradient at that point. So this is the main idea of gradient descent algorithm. So that we have discussed last lecture. So the update rule we have got. So for that update rule, first you need to compute the slope or gradient of that cost function. So any cost function, if it is given, analytic function is given. So for that analytical function, we can get the slope. And then you can update in this way. The Wn plus 1 should be Wn minus mu into Gn. Okay, where mu is called learning rate or step size. Right. And in previous lecture, we have considered this analytical cost function. So in this video, actually we'll consider again 1D optimization problem, but this time we'll consider the samples, more realistic cost function we can define. Okay, so one realistic system is given where the data set is provided, sets are provided, and we can define corresponding cost function that will be discussed in detail here. And basically we'll be considering two problems, one problem from machine learning that is called linear regression, and another one is from adaptive filtering, and that will be called as system identification or channel estimation. And we'll discuss gradient descent algorithm to obtain the optimized solution. With this, we'll also show the analytical solution and we'll give the MATLAB simulation results, and that will be shown step by step clearly. Now, consider the regression problem from machine learning. Suppose we want to understand the baby's weight with respect to its age. So we have collected one data for a certain baby, and when baby was at the age of 1 year, that time suppose his weight was 8.8 kg, and second year means age of 2, the weight was 11.9, and then age of 3 11.2, and 4 12.9, and 5 16.6. Only 5 data we have considered here. We want to discuss the linear regression problem with the help of this data. Thus only we have considered very few number of samples. Now here you see in second year its weight was 11.9, in third, at the age of 3 years it is reduced to 11.2. It may happen somehow, but as we expect that as baby is growing, its weight should increase linearly. So the weight and the age should have some linear relation, but this one, it shows that it is not strictly linear. Obviously it cannot be a linear one. But again, if we try to get some linear relation between this age and weight, then what we will do, right? So first we'll try to plot this data. So this x-axis is the age, and y-axis will consider the weight in kg. So this is the first sample, when age is 1 and weight is 8.8. The second sample, age is 2 year, second year, and weight is 11.9. The age is 3 years, and then it is 11.2, 4 years, 12.9, 5 years, 16.6. Right? Now, we'll try to fit a line. We want to get a linear relation between these two axes, x-axis and y-axis. So we can try to fit a line, best line, but obviously the points, through the points we cannot make a single line because of this abnormality here. Okay, so there will be some, suppose this is the best line we can fit, right? And this best line, this y equal to mx plus c, m is the slope and c is the offset, we can say, or cut off this point, okay, where it will cut the y-axis when x equal to 0. That is also called bias term. Okay, so y equal to 2x plus 6, suppose this is the best line we can fit for this data set, suppose, right? Now for this data, obviously you see whenever we will try to fit this line, this is the error when at a age of 1, this line will give you this value, but exact point is here. Okay, so this much error you will get here, again this much error you will get, so this is the error here, this much error you will find here, and this much error you will find here. Okay, now so again this is the suppose best model or best line that we can fit. Now we'll try to understand what we can conclude from this linear regression problem. Now suppose if the problem is that this kind of problem, if we get that, find baby's weight at the age of 4.5 years. But in this data set, this 4.5 is not mentioned. Okay, so at the age of 4 years, it is 12.9. At the age of 5 years, it is 16.6. But at the age of 4.5, that value is not given. So we can expect that the value will be in between this 12.9 and 16.6. So if we can have one linear relation, some kind of relation between age and weight, then from that function, if we put x equal to 4.5, we'll get certain value of y. Means we can interpolate all the values, intermediate values. So this is the advantage of linear regression. So actually, regression analysis, it's an interesting topic in statistics. We can conclude lots of things from linear regression, but for one-dimensional problem, we can conclude that at least we can find out intermediate values from the linear functions. Okay, we can predict certain values. Like this one at 4.5, from this curve, we can find out this point. Okay, you see, so if I take a vertical line, it will cross here, and that time this value is suppose 15. So that value also we can calculate from the equation, because the equation we have considered y equal to 2x plus 6, and here we replace x by 4.5 because we want to find out the weight at the age of 4.5. So 2 into 4.5 plus 6, that is 9 plus 6 equals to 15. So we can predict that the weight of the baby at the age of 4.5 years, it was 15 kg. So this kind of intermediate values we can find out from, if we can have some linear regression function, right? Now we'll consider this regression line. Okay, So this function y equal to 2x plus 6, here x is the age input and y will call it predicted weight. Okay, so at the point, those points, suppose it is mentioned already in data sets like x equal to 1, 2, 3, 4, 5, their actual values are given. Okay, like suppose x equal to 1, actual value is 8.8, but the predicted value will be here. At the age of 2, second year, this is the predicted and this is actual. So this much error you will get. That is called residue. So we can mention some residue. Residue means actual weight minus predicted weight. So residue or error. Okay, so we can calculate at the sample points. Okay, so we can find out total square of the residue. Okay, so we can find this residue. So here it is 0.8, here it is 1.9, and here it is minus 0.8, here it is minus 1.1, here it is 0.6. So I want to find out total error. So we should not take only the summation of these errors, because sometimes it is positive, sometimes it is negative. It may cancel out. So to get always positive magnitude, we should first take square, then add it up. Thus, we'll consider total square of residue. So that we can calculate. So for this one, we can calculate all, we can add all those things. Suppose we are getting 6.46. Now, if total residue, square of the residue is 0 somehow, then obviously we can conclude that all the data point will lie on a baseline. Okay, there is no error at all. The points are on the line only. Okay, so that time, every time we will predict the exact one. But when the points are, we cannot fit a single straight line passing through all the points, then obviously you will get certain errors. But if this total square of the residue is low, very low, then we can say that the linear regression may work. So we can go for linear regression. It can fit it. Okay. So there are lots of things in linear regression problem. One is called underfitting, other one is called overfitting problems. So those will be discussed in detail in some videos. So here our objective is to find out the gradient descent concept for the regression problems, this kind of problems. Okay, right. Now, so our for regression, linear regression problem, we'll choose in this way that y, we'll consider yp. P stands for prediction. Okay, so yp will be of this form: mx plus c. M is the slope and c is the bias. Okay, so we can start from any value of m and c. So this is the initial guess if you start with, and that can give you huge error. Okay, because it is not going through the points. So if I consider this one, then this is actually 2D problem, because we don't know what is the value of m and what is the value of c. So these are the two unknown values that we need to find out. So actually it is a 2D problem. Okay, and you see, this is the errors, corresponding errors we have shown here. So what we can do, we can define our cost function in that way, the total square of the error, and we can divide upon by n only. If there are n such samples, and then if we divide by n, then it will be called as mean of square of error, mean square error, MAC. So we can try to minimize the mean square error, where this error EI is actually this y of I, means actual data value at the ith input, and that time this is your predicted one, yp of I. So that difference is your E of I. So for this one, this is the your E of I, E of 1. This is your E of 2, this is of E of E3, E sub 4, is a 5, this length. Okay, and this is your predicted one. Okay, so our objective is to minimize this mean square error. We need to find out that corresponding AM and C. So actually it is a 2D problem, but if we assume that C is 0, then we'll try to fit only by slope, then we can convert it to 1D problem, but that may not give you the best one. Okay, right, so we can convert it to 1D problem, but linear regression, the lowest one we can consider for this 2D problem. Actually the slope and bias both you need to compute it, right? Now I'll give you one more problem from adaptive signal processing perspective. Now here we'll consider one input sequence xn, and our unknown system is having a single tab, that is tab value is W naught, and the observation noise is Vn. So this total unknown system will produce this output Dn. Okay, so here this Xn and Dn, these two will be available. Okay, for this unknown system, so we don't know what is the Wn, W naught, and what is Vn. And Vn is actually random sequence, but its magnitude is we'll consider very low. Now we'll have this relation Dn. Obviously we can consider that this xn is multiplied by W naught, then Vn is added, so it is W naught into xn plus Vn, that will be your D of n. So D of n is the output, and here x of n is the input, and W naught is actually unknown filter coefficient that we need to find out, and Vn is observation noise, random noise. Now this is the unknown system, and this data sample xn, input sample, and corresponding output sample Dn, suppose these two are available, samples are available, and from these two samples we need to estimate this filter coefficient W naught, so that will be here. Okay, so this is your xn, this is your yn, and we need to estimate this system coefficient, single step coefficient, and suppose this step value is W, and it will produce yn. So in that case Dn minus yn will be the error En. So our objective will be, or we can define our cost function as this one. So if we have infinite number of samples, that means all the statistics we can compute about the input statistics xn and the cost correlation between Dn and xn, everything we can compute from this infinite number of samples, and in that case we can define our cost function as expected value of square n. Okay, so that we have discussed in my previous lectures. So this is for infinite number of samples. There we can define this kind of cost function, and when we'll have some finite samples only, there we can go for this kind of cost function. Suppose there are m such samples, so we can consider mean of square of error. Okay, so 1 upon m and summation of square n, square of n equal to 1 to capital M, right? So there are m number of samples, finite samples. So these two cases we will consider, and for both the cases we will discuss the analytical solutions and the corresponding, and especially for the finite solution we will consider gradient descent algorithm, right? Now consider first the infinite number of samples where the statistics of samples are available. Okay, that we are assuming. So this is our system model. The unknown system coefficient is W naught. This is Vn, that is added. So dn and xn, these two are available. And the relation is dn equals to w naught xn plus vn. Now, we want to estimate this filter coefficient w, which will produce minimum mean square error or expected value of square n. This cost, so here en is this one, dn minus yn, and where yn is simply w into xn. Okay, so we'll consider this cost function j equal to expected value of square n. So here we replace this en up by dn minus w times x of n here, and that's square. So if I expand it, I'll get expected value of d square n, and here middle term will be 2 into w, and you see w is independent of n, so I can take outside. Then I can consider expected value of dn and xn only, and last term w square we can take outside, then expected value of x square n. So this is our cost function, and from this cost function, so here we'll consider this expected value of dn xn as p, and we'll consider expected value of x square n as capital R. So this small p is called cost correlation value between dn and xn, and x square n is the variance actually. Okay, and we'll consider that xn, its mean value is 0, right? So for optimization thing, what we'll do, first we will consider the gradient or slope. So we'll find the derivative of this j, so dj upon dw. So that we can, so first term is independent of w, so its derivative is 0. Second term, this w derivative is 1, so it will give you minus 2 into p. And second one is derivative of w squared is 2w, and then r is multiplied. So this is your slope. And for optimal solution, suppose w equal to w star is the optimal, means minimum point. So at that point, derivative should be 0. That is a constant. So we can solve for that. So we can put this one 2 minus 2p plus 2w star r equals to 0. So if you solve, we can solve for w star. So 2 will cancel out. So it will become p upon r. That means expected value of dnxn upon expected value of x square n. So this is one interesting result for infinite number of samples. Okay, it is simply p upon r, expected value of dn xn upon expected value of x square n. So if you can have this statistics and this one, we can compute the best one. Now it is interesting, we are interested that to know whether this w star is actually same as w naught or not. Okay, because our objective is to find out this unknown filter coefficient w naught. So we will get the best one is w star, and we can show that for this one, this w star is actually w naught, nothing but w naught, and this is called unbiased estimation. There is no error, though there is one additive noise Vn. Okay, so Vn is added, random signal Vn is added, yet we can estimate this w naught perfectly if all the statistics are available. And this is because whenever you will use the expected value, as it is a random, its effect is nullified. Okay, so if you take average value of those things, so its average value is 0, thus you will get w star equal to w naught. So that we can prove it. So its proof is very simple. Now consider this thing, dn equals to w naught xn plus vn. Okay, this is from this equation, this system equation. Okay, dn is the output, xn is the input, w naught is the unknown filter coefficient, and vn is additive noise. So W naught into Xn plus Vn is Dn. Now multiply both sides by Xn, both sides, right? So what you will get? Left side Dn times Xn, right side W naught Xn into Xn x square n, and here it is Vn times Xn, right? Then take X factor operator on both sides. As the X factor operator is a linear operator, so we can take individually. So this is the X factor operator on this one, this is one, and this is one separately, right? Now we'll focus on this one. So this is our equation now. Now we'll proceed. Now here we can simplify it as, so this left side is same as expected value of d and xn, and here omega naught or w naught is constant independent of small n, so it is outside. Expected value of x square n only we can consider, and here this xn and vn, they are independent and both are random. Okay, independent random. Okay, so we can take expected operator, this one, that expected of xn multiplied by expected value of vn, and also we'll assume that this vn and xn both are having zero mean. Its mean value is 0. So if its mean value is 0, its mean value is 0. So if any one is 0, then it is sufficient. Then this value is becoming 0. The second last term will vanish. Okay, with this condition that this observation noise is having 0 mean. So under this condition, this term is exactly equal to w naught into expected value of x square n. So what you can do, you can divide this by this, it will be equal to w naught. That imply that, you see, this factor is same as this one. So this is basically w star. Thus we can say that w star equals to w naught. So it's an unbiased estimator. So even though additive noise is there, we can perfectly reconstruct or estimate the unknown coefficient w naught. This is the beauty of this analysis. Okay, so this is for infinite number of samples. Now let us consider finite number of samples for the same system. Okay, so same this one unknown system, and suppose again we want to estimate this one by w, and in this case the samples are finite, so we'll go for this kind of cost function. The j will be mean square error, so 1 upon m times summation of square n equal to 1 to capital M. Now for this one again we want to find out optimal solutions analytically. Okay, if I want to get the analytical result first, so can you guess what kind of analytical result you will get? So you see w star we obtained equals to expected value of dn xn upon expected value of x square n for infinite number of samples. So for finite samples, what should be your w star? Okay, so we can guess that w star will be of the same form. Okay, so what should be numerator and what should be the denominator? So you can guess a little bit. So it is the expected operator of this one, and here expected operator of x square n. So numerator should be similar to that one, dn and xn, and denominator should be similar to xn, x square n. So actually you'll see we'll get w star will be equals to the simple summation of dn xn upon summation of x square n. Actually we can divide by 1 upon m and 1 upon m here, but this 1 upon m will cancel out, so you will get this ratio. So this ratio will give you optimal solutions. So exactly similar way we can find out these optimal solutions. So very quickly we will discuss this one. Okay, the proof. So you see this is your cost function. So we can replace en. So en is basically dn minus yn, and yn is w into xn. So dn minus w into xn. This is your en, that's square. Okay. So if we expand it, we'll get these 3 terms, again similar to earlier. So only thing is that here is summation, discrete summation. So this term is there. Second term, this w, it's outside, I can take 2w. And here w squared term will be there, and with this one. So this cost function, now we can find the gradient or slope, so dj upon dw. So first term is independent of w, derivative is 0. Second term, derivative is, this value is 1, then it will become minus 2 upon m times this one. This is independent of w, that will be there. And derivative of w square is 2w. This is 1 upon m times summation of x square m, right? Now to get this optimal solution at w star, this derivative should become 0. So if I put this one w star here, and if I make it 0, you see 2 upon m will cancel out. So this upon this will give you w star. So this is a fantastic result. W star is basically sum of dn xn upon sum of x square n. You will get analytical result. So for 1D problem, it is very easy to find the analytical solutions. But our objective is to get the iterative solutions using gradient descent algorithm. That is the objective for this video. Okay. Now let us see, using the gradient descent algorithm, whether we will be able to get this analytical function value w star exactly or not. Right. So we'll go for gradient descent approach for finding optimal solution. So we'll consider the finite sample. So this is the cost function as we defined earlier. And for this cost function, we can get the gradient or slope that already we have discussed. And we know the update rule. Update rule will be wn plus 1 should be equals to wn minus mu1 or some step size times the gradient at that point wn. Okay, so that we can replace here, right? So what you will get? So if I replace this thing here, so this will consider as p, this 1 upon m times the summation I'll consider as small p, and 1 upon m times this summation square of x square of n, that will consider as capital R. So if I consider this thing capital R into w, and this is your p, and this 2 into mu1, that we can combine together, and 2 mu1 I'll consider new step size mu. Then you will get this simple update rule. Okay. So you see, every time wn is different, every iteration wn is different, p and r would remain constant. So with this formulation, this is one advantage, that you can just replace wn here. So this term you can compute every time, and you can add with previous wn, will get new wn. Okay, this is one way to calculate the gradient, right? Now we can have alternative approach. Directly we can find out the gradient for this cost function. So if I take derivative of this j with respect to w, right? This is 1 upon m times the summation is there. So here this e square n, there we need to take a derivative. So e is basically function of w, right? So what you do? We'll take derivative of this square n. It will be 2 of en times dw of en. Derivative of en with respect to w, we should multiply it, right? Now e of n is basically dn minus w into xn, right? This is your en, this is the target one, actual one, and this is the predicted one, right? So we should call it better the e is of w of n, because it's also a function of w. So actually it is dn minus w times xn. So if you take derivative of this one, then this is 0, and its derivative is minus, derivative is 1, so it's simply xn. So this one we can replace by minus of xn only. Okay, so this is your derivative, right? So you see, this is the update rule. Wn plus 1 equals to Wn minus mu1 times dj dw. Okay, so here we can replace by this one. So then this 2 mu1 upon m, that also we can combine together. We can consider a single step size mu. So if I consider this, then we'll get this kind of update rule. Wn plus 1 will be Wn plus mu into sum of Ewn into xn, right? And this form is interesting form. So actually from this form, so here you see every time we need to calculate the error for each sample for that point Wn, and you should multiply with corresponding input data xn, then sum it up, right? So we can show that from here we can derive least mean square algorithm, the most popular adaptive algorithm, that is Wn plus 1 equals to Wn plus mu into simple En times xn. Obviously, this is for the single tap. If it is having more than one tap, then this Wn will become a vector and this xn will become a vector again. So that will be discussed later in detail. Okay, but we can derive this least mean square algorithm easily from this update rule. So basically, if we consider stochastic gradient descent, if we start with stochastic gradient descent as GD, then easily we can get least mean square algorithm. Okay, so we'll be discussing stochastic gradient descent in some course, in some video in detail. Okay, so keep watching. So this is the update rule. So we have got the update rule for 1D problem. Now we'll go for simulation result directly. So MATLAB, go for MATLAB simulation results. So this is the finite number of sample problem. So this is the unknown system. Dn and xn, these two samples are given, data sets are given. We need to find out this w, which will be close to this w naught, right? So exactly, so from this figure, we will find out, we will consider the optimum filter coefficient w naught. Suppose it is given, but this is suppose unknown. So let us consider that this w naught equals to, suppose this is, we can consider 0.5 for example, right? And with the help of this one, this w naught, now considering the Vn is random signal, white noise, we can generate the Dn, generate the input sequence xn, and we can get corresponding Dn. So we can generate this data Dn and xn. And suppose this Dn, xn, these are available, then we'll try to estimate this unknown filter coefficient w from this model. Okay. So here we'll consider this cost function, the mean square error, and basically we'll try to update in this way. Wn plus 1 will be Wn plus mu into p minus Wn Rn. So this form I have considered here. Okay, so p is this term and R is this term. I hope it is clear. Now we'll see the MATLAB code and how weights are evolved. Okay, this Wn is changing over iterations that we want to observe. Right. So for simulation, we'll try to basically fit a line, that is this y should be equals to w into xn, and we're expecting that this wn actually it should move towards w star at least, and w star is the analytical result. Okay, so it should move toward that one, but w star may be different from w naught for finite samples. Remember, We have shown that for infinite number of samples, W star is same as W naught. But for finite number of samples, W star may be different from W naught, but it should be close to W naught, right? Now this is the code I have written. So here you see I have generated one input sequence in regular way. It is not actually random because I want to show the plot. Okay, I want to discuss the data set. So that's thus we have considered one regular interval xn. So first x of 1 is minus 2.7, then minus 1.3, 0, 0.7 and 1.8. But Vn I have considered random sequence, and this optimum unknown filter coefficient I have considered 0.5. So first I will multiply these two, W naught and x, and then we'll add the V, I'll get D. Okay, so this data set is now available. So that will show you in tabular form. Okay, and then we have considered step size and initial point Wn I have considered 0. Then iteratively we will compute the gradient G equals to minus P minus Wn times R. This is our gradient value. Okay, and that gradient, so the update rule will be Wn equals to Wn minus mu into G. That's simple. Okay, so rest things, all the things I have added here, so that from the simulation only we'll get all the values. Okay, this is only for teaching purpose. Okay, but algorithm is very simple. So if anyone wants to get this code, so you can write an email to me, I can share with you, right? So first I will consider step size mu equals to 0.15, right? Now you see, so this is the samples we have generated. Okay, these are samples. You'll see I am showing the samples here, right? This is the x-axis, this is the D, and we want to fit a line there, right? So here I have considered only 5 samples, so I want to fit a line here, right? And obviously y equal to mx only, there is no c, right? So here you will see this one. So initial value I have considered here is 0, and I have calculated all the values. So p I have considered here, calculated here. So p, you see, it is a summation of d and xn only, and the average value of that. So that I have considered. You just multiply these two, the corresponding only. These two you will multiply and then add all those things, and then at the end divide by this number m5, you will get p value. And AR is a summation of x squared n upon capital M. So this x values, this one you will take square and then add. So I have taken square of x values, I have taken addition, and then at the end I have divided by 5. I have got this one. This is R. So the optimal analytical value W star is this one. Okay, so that you can note. So for this one, you see W star is actually, it is giving us 0 point, so this is minus e to the power minus 0.01, it is given, so it is 0.438, this one, right? And W opt, exact value we have started with 0.5. So you see they are not same. Okay, for this data W naught and W star, it's not same, but iteratively at least we expect that the gradient descent algorithm should produce this W star. It may not give you 0.5, but it should approach to W star. So initially we will start with W0 equal to 0. Okay, now this is the initial value. Okay, so that means this is d equal to 0 always. D equal to wx, w equal to 0. That means d equal to 0. So this is the horizontal line we'll start with. Right. Now you see, this is the first iteration. You consider this one. This is the first iteration. Iteration number 1. There we will compute the g minus p minus times p minus wn times r that we have computed here. Then we have updated w. So w initially it was 0. Now it is moving to 0.167, that one. So this is the equation. This is the line it is showing. So slope is right now 0.167. This is the slope, right? Okay. Now you can go for the second one. Iteration 2, you see the it is updated, Wn is updated to 0.27. So slope is now increasing. Okay. So you see the slope is increasing here. So from 0 it is then here, right? So you see iteration number 3, it is increased. Then it is 4, 5, it is moving this side. So this, check the value. It is 0.432. Okay, 0.434 at 10. Right? So it is very close to W star. W star is 438. So here also I have plotted these two. So this is their level, minimum level, and cost function is reducing gradually and it is converging to this level. And this, you see the slope is increasing gradually starting from 0 and it is coming to this level. And this is the best fittings we'll get. Okay, so if we go for more iterations, probably we can get exactly W star equals to 0.438. Okay, just we have gone for 10 iterations, we have obtained up to 0.432, something like that. Okay, right. Now next one, if we increase the step size, then obviously we will move quickly. But I told you last class that it may give you some overshoot and undershoot. Let us see whether with this step size it will give that kind of thing or not. Okay. So again we have generated one data here, samples, different kind of samples, not the same samples. Okay. And you see with this step size what is happening. The same thing will repeat. So we start with this initialization. Then second one is coming here. Third is here. Okay. You see it is overshoot and undershoot. But it is gradually moving towards this value. And this time its value is 0.52, this optimum value. And you see I have plotted both the things. This is the baseline we have got, and this is the cost function how cost is reducing over iterations, right? Now we'll consider again higher, 0.9. I told you that you cannot expect that if you increase the step size you will get better convergence rate always. Okay, so it may diverge, so you have to be careful. So I want to show that one. So this mu equal to 0.9. Check this one. This is the data set I have generated, right? Now see, this is the optimum 4.77. Now this is first iteration here suddenly. The second iteration is opposite, negative. W is negative. Then again positive, high value. again negative, minus 0.8, the positive 2. So you see the function, the slopes are actually growing, positive and negative, positive and negative. So exactly it is unstable, diverging. You see the cost value over iterations, it is growing. Okay, so we cannot use step size 0.9 for this problem. Okay, so this is one issue, how to choose this step size mu. So that will be discussed in detail in the next lectures, how to find the optimal step size, especially for the higher order gradient descent algorithm. Okay, so in upcoming video we'll discuss this thing, the higher dimensional problem, the dimension 2 and more, and main focus will be on the optimal step size, and also we'll give you the MATLAB simulation results, and I'll show you step by step how it is converging. There I'll consider the contour plots, everything. So please keep watching. I'll there consider one analytical 2D problem, and I'll also show one linear regression 2D problem from machine learning. Okay, so keep watching. If you like this video, then you may share it to your friends or your relatives, and you may subscribe my channel as well. Thank you.